Welcome to The Explainer. Today, we're popping the hood on large language models to see what's really going on inside. We're going to track a prompt's exact journey, literally from the second you hit enter, all the way down the assembly line to the final generated word. You know the feeling, right? You type a prompt, wait a fraction of a second, and miraculously you get this perfectly human-like response. It feels like magic. Or, maybe it feels like there's a tiny, incredibly fast librarian inside the machine, frantically digging through a massive encyclopedia. But we really need to dispel that illusion right now, because that is not what's happening at all. J.D. Meyer really hits the nail on the head here. As he puts it, an LLM does not search, retrieve, or reason like a human. It just predicts the next token. It's essentially a meaning-aware autocomplete built on massive pattern recognition. We naturally want to project human reasoning onto these things, but once you stop thinking of the model as a thinking machine and start seeing it as a highly advanced pattern engine, the whole process starts to make perfect sense. So, to truly understand this factory-like process, we're going to trace your prompt through 5 specific stages: the inference illusion, tokens and embeddings, the power of attention, KV caching, and finally, the decoding loop. Let's get right into it. Step 1. The inference illusion. We need to separate how the AI brain is built from how it's actually used. People mix these up all the time, so let's be super clear. Training is the massively expensive learning phase. You're churning through mountains of data on huge GPU clusters for months just to dial in billions of parameter weights. Inference, which is what we're focused on today, is the real-time application phase. In this phase, those learned weights are completely static. They're just being used to efficiently predict the next token based on whatever prompt you just gave it. Okay, moving to step 2, chopping and mapping, translating human words into machine math. Imagine throwing a raw, basic prompt onto the assembly line, something like the cat sat on the, well, here is the high-level roadmap of what it goes through: tokenization, embedding, attention, and generation. Let's unpack that very first step. Your prompt isn't actually read as words. The model literally chops your text into smaller pieces called tokens. And it doesn't just use whole words, because that would break every time it saw a typo or a brand new word. Instead, modern LLMs use subword methods, like byte pair encoding. So a big word like unhappiness might get sliced into un, happy, and ness, with each piece getting its own integer ID. It's a brilliant way to handle endless language variations without needing an infinite dictionary. Now here is where it gets wild. Those token IDs get transformed into embeddings. The model maps them into this dense, high-dimensional numerical space where concepts with similar meanings literally live right next to each other. It captures semantic relationships so perfectly that you can actually do math with human concepts. Like, if you take the vector for king, subtract man, and add woman, you land in a space incredibly close to queen. This embedding step is absolutely crucial. It's the bridge between our language and the machine's math. Which brings us to step 3. Connecting the dots. Let's talk about the absolute power of self-attention. Once our tokens are embedded as numbers, the model has to figure out how they relate to each other in the specific context of your prompt. Enter the transformer architecture and self-attention. Unlike us, it reads the whole sequence at once. It projects every token into query, key, and value vectors. Basically, the query is what a token is looking for, the key is what it contains, and the value is the actual content. By comparing these, it figures out what matters. For instance, in the sentence, the animal didn't cross the street because it was too tired, self-attention mathematically links the word it straight to animal and definitely not the street. It's evaluating all these different relationships all at the exact same time. All right, step 4, the memory hack. Overcoming the prefill bottleneck with KV caching. Right here is where our factory floor usually hits a massive traffic jam. You see, inference is split into 2 distinct phases. First, you have the prefill phase. This is heavily compute-intensive. The model digests your entire prompt all at once to generate those key and value vectors we just talked about. And it scales quadratically, meaning a slightly longer prompt requires way more math. Then there's the decode phase, which is fast, generating just 1 token at a time based on the context built during prefill. So why does this matter? Just think about this number. 40 gigabytes. A single 128,000 token context prompt on a 70 billion parameter model eats up roughly 40 gigs of incredibly scarce, super expensive GPU high bandwidth memory just to store those prefill key and value tensors. Imagine hundreds of employees asking an AI about the exact same massive company document. Without a fix, you'd be burning insane amounts of GPU compute just recalculating the exact same context over and over again. So, to avoid wasting all that time and money, Enterprise systems use KV caching. They take incoming prompts, chunk them into token blocks, and securely hash them using algorithms like Blake3 or SHA-256. That security is absolutely key, by the way, so one user doesn't accidentally pull someone else's private data. If it finds a secure match, the system grabs this cached scratch space from a fast-distributed storage network like FlashBlade and instantly injects it back into the GPU. It elegantly turns a brutal math problem into a lightning-fast storage lookup.
Finally, step 5. The output loop, seeing autoregressive decoding in action.
The context is mapped, analyzed, and safely cached. Now, the assembly line shifts into high gear. The model uses autoregressive modeling. Simply put, it predicts the next token based on everything that came before it. It takes that entire cached state and calculates a massive probability distribution across tens of thousands of words to pick the exact right next token.
Let's watch this play out. The model looks at our initial prompt. The cat sat on the...
Boom. Based on the math, it predicts mat. It tacks that onto the sequence, and from then on, it treats that word exactly as if you had typed it yourself. Then, the loop fires all over again, predicting because. This insanely fast cycle repeats token by token, hundreds of times per second, until it finally generates a specific stop token or hits a length limit. But wait, it doesn't always blindly grab the number one choice. Depending on what you want, it uses different strategies. Greedy decoding simply picks the absolute highest probability token every time. Super fast, but kinda robotic. Beam search explores multiple top sequences simultaneously to build better overall sentences. Or there's nucleus sampling, also known as top P, which dynamically pools highly probable tokens and picks randomly from within that pool. That's what gives the AI that creative spark and makes it sound so natural. So now that you know the exact journey from a simple token to fully generated text, it leaves us pondering a pretty massive challenge. As these models scale up to trillions of parameters, how are our GPUs and storage networks going to keep up with the insatiable memory demands of this AI assembly line? It's going to take a major infrastructure evolution for sure. Thanks so much for joining me on this explainer, and honestly, I hope you never look at a blinking text cursor the same way again.